Welcome everyone to a worked example for the method of variation of parameters. So hopefully you've already had a look at the video on the theory behind this, so you'll know what the formula is that we're trying to apply. And we're just going to jump right into solving this problem, which you've seen before. So we have a system of two linear equations here, an initial value problem. We have initial values over here. So y1 prime equals y2 plus e to the t, and y2 prime equals y1. So because of this e to the t, this is a non-homogeneous system, and we're going to need to do something like the variation of parameters in order to solve it. So here we go. The first step, of course, is going to be writing this in vector and matrix form, and that's pretty straightforward. So we can say that we have here y. We don't want to start with blue. I'm going to start with black ink here. So let's zoom in a little bit. All right, so we have y prime equals, and now for the linear part, here we have 0 and 1 for 0y1 plus 1y2, and then 1 and 0. This will all be multiplied by y, and then plus e to the t 0. All right, and so that's our starting point. That's the equation that we're trying to solve. It's non-homogeneous because of the e to the t 0 hanging out there on the right-hand side. And we're going to try variation of parameters. The first step in the variation of parameters is that you have to have a fundamental matrix. To find a fundamental matrix, we need to find two solutions of this, the linear version of this equation. So we're going to have to solve the eigenvalue problem. Right? So we have our matrix. We're going to subtract lambda down the diagonal. So we have negative lambda 1, 1, negative lambda. And we're going to be taking the determinant of that. That's lambda squared minus 1, setting that equal to 0. We see that we have eigenvalues of lambda equals 1 and lambda equals negative 1. We also need an eigenvector to go with each of those eigenvalues. So we'll deal with lambda equals 1 first. The matrix we're dealing with here is negative 1, 1, 1, negative 1. And we're going to multiply that by v1, v2. It has to come out to be 0, 0. All right, and we can see pretty directly that the matrix, the vector 1, 1 will do the job. And then for lambda equals negative 1, we're going to subtract negative 1, so that makes it 1, 1, 1, 1 is our matrix times v is equal to 0. And here we can see that the vector 1, negative 1 would do the job. So from these eigenvectors together with our eigenvalues, we can make solutions. The first one, now we can do this. Our first one will be the solution e to the t times the vector 1, 1. And the second one will be e to the minus t times the vector 1, negative 1. Right, it's e to the t because it's e to the lambda t, so e to the 1t, and then e to the minus t because it's e to the negative 1 times t. Those are two solutions. We can multiply them in and get vector forms. So we have e to the t, and we have e to the minus t minus e to the minus t. And now taking those, our next step is to form our fundamental matrix. The fundamental matrix will be a matrix composed of these two things as the columns. So we would do something like e to the t, e to the t, e to the minus t, minus e to the minus t. Now, you could have done those in the reverse order. You would get a different fundamental matrix. And that would make all the steps that we're about to do look a little bit different, but at the very end, it should all come out the same because there is a unique solution to this initial value problem. So no matter which method we choose to get there, we're going to end up at the same place. All right, so now we are going to try to use this fundamental matrix to solve. So that's the problem again. So we're going to be working with this. So let's recall what our fundamental matrix is. So C of t equals e to the t, e to the t, e to the minus t, minus e to the minus t. And our variation of parameters formula is a little bit cumbersome, but it's, we got to know how to use it. So remember that we have y of t equals c of t, c inverse of t0, y0, plus c of t integral from t0 to t, c inverse of s, g of s, ds. That's a lot of stuff. That's an awful lot of stuff. You can see we're going to need a few things here. So one, we have c of t. We're going to need, in a couple of places, we're going to need c inverse. So we need the inverse there and in the integral over there. So our first step is going to be to just calculate what that inverse is. So since this is a 2 by 2 matrix, it's not so bad. We have to find first the determinant of the fundamental matrix, so let's do that. I didn't mention, how do we know that this is a fundamental matrix? We can do that by calculating the Wronskian, taking the determinant, or because these two solutions have different eigenvalues, we automatically know that they're independent of each other. So we don't have to go through too much extra work. To calculate the inverse of C, we're going to need to know its determinant. That's part of the inverse formula. So let's quickly do that. The determinant of C of t, we are going to be cross multiplying. So we get e to the t times minus e to the minus t. Those cancel, you get just minus 1. And then on the off diagonal, you also get 1. So we end up with minus 1 minus 1 for a determinant of minus 2. And now we can write our inverse matrix. C inverse of t will be 1 over that determinant, so 1 over negative 2 times, and how do we do the inverse? Well, we swap the diagonal elements, so this becomes minus e to the minus t, e to the minus t, and then we put negatives on the things on the off diagonal, so it's minus e to the t and e to the t. And if we bring this minus sign in from the constant out front, we could rewrite that as 1/2 e to the minus t, e to the t, e to the minus t, e minus e to the t. All right, I don't want to bring the constant 1/2 in there. That just complicates things a little bit, makes it a little bit uglier. So we're going to just leave it in this format here. All right, so now the next step in the formula, we're going to work on the integral from the inside out. So we have the inverse matrix here. We're going to have to multiply it by g of s. That's going to give us the integrand. So that's going to be our next step. We'll see how that goes, and then we'll integrate the result. All right, so C inverse. Let's clean that up a little bit. So C inverse of s g of s will be 1/2 e to the minus t, e to the t, e to the minus t, minus e to the t, times g, which is e to the t 0. All right, we multiply that out and see what we get. And so we still have the 1/2 out front, taking the first column times the given matrix, and we get just e to the minus t times e to the t is 1. And then the second row times the column, we get e to the t times e to the t, so that's e to the 2t. Now, I have made a mistake here. I'm going to correct this really quickly. All of these places where I've written t, I should have written s. So we're going to have to go through and clean that up just a little bit. Sorry about that. S, almost did it again. S, 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 and 2s. All right, so that's the inside of the integral, right? Remember up here. So we're going to have to integrate this thing from t0 to t. t0 in this case is, right here, is 0. So it's going to be an integral from 0 to t. All right, so let's get on with that. So we do the integral from 0 to t of c inverse of s, g of s ds. We get the integral from 0 to t of 1/2 times 1 e to the 2s ds. So the vector here will be, we're going to do antiderivative, just component by component. So we get s and 1/2 e to the 2s. We've got our 1/2 out front, and we're going to analyze this from 0 to t. So we get, in the end, we get 1/2 in front. The top will be t minus 0, so t. The bottom will be 1/2 e to the 2s minus 1/2. All right. So just to not have quite as many fractions floating around, let me just go ahead and pull out another 1/2. So this becomes 1/4 times 2t and e to the 2s minus 1. Okay, so we've gotten that far in our formula. We've got this whole portion here taken care of. Next step is working out is we're going to have to multiply by c of t. All right, and see what we get when we do that. All right, oh, I have, again, not done the right thing. This s should be a t. So let's clean up just a little bit. So 2t minus, and this s over here should be 2t. There we are. Okay, so getting back on track, we need to multiply this thing by c of t, the fundamental matrix. All right, let's do that on a separate page. So now we're looking at c of t times this integral that we just did. So c of t was e to the t, e to the t, e to the minus t, minus e to the minus t. And we're now multiplying that by 1/4 times 2t and e to the t, 2t minus 1. All right, our 1/4 can go out front. And we just need to do some row times column calculations here. So let's see what we get. We get, we're going to have 2t times e to the t. And then we have e to the minus t times the second entry in the column. So that will be plus e to the t minus e to the minus t. Let me just check my work. Yep, that looks fine. And then we're going to do the same thing in the second row. So we have 2t e to the t. And then we have minus e to the t plus e to the minus t. All right, and that's the entire second term there. In the first term, so the variation of parameters formula, recall, let me just jump back here real quick. So we've just finished calculating this entire bit over here on the right. We still have to do the part that comes from the complementary solution up here in the front. So c inverse of 0 times y, 0, the initial condition. All right, so getting on track with that, we need to know c of t times c inverse of 0 times y0, the vector y0. And we have all these components, so we can just write them out. So this is, again, e to the t, e to the t, e to the minus t, minus e to the minus t. That is the fundamental matrix. Then times its inverse evaluated at 0. So hopefully you have that in your notes. I'm going to just write it down. That will be 1/2. And then when we put in all of those entries, it will be 1, 1, 1, minus 1. And then finally, we're multiplying by the initial conditions, which are 5/4 and negative 1/4. So those go in here and here. So we just have to multiply this out, and we'll have the second component of the variation of parameters formula. ready to go. So which things do we want to multiply first? I think what I'm going to do is pull out a 1/4 from everything. So I have the half. I'm going to pull out a 1/4 from that thing at the end. So I'm going to have 1/8. Still have this matrix e to the t, e to the t, e to the minus t, minus e to the minus t. And then we're going to multiply this out. So 1 times 5 plus 1 times -1. We're going to get a 4 here. And then 1 times 5 plus -1 times -1. We'll get 6 there. Okay, almost there. So now 1/8 times, now we multiply this matrix times the vector, so that's going to be 4e to the t plus 6e to the minus t, and 4e to the t minus 6e to the minus t. That's the second part of the variation of parameters formula. So that's all multiplied by that 1/8. We can pull that in and take these two components that we have together. That will give us our unique solution. So just to point this out, what we're going to be doing is adding this part as part 1 and this part up here as part 2. Those are the two components of the solution. When we sum those two together, we will have ourselves the unique solution to the initial value problem. And I'm going to do that and simplify it a little bit just so we have a nicer version of this in the end. So hopefully you got all that down. We'll go for one more page here, if all goes well. There we go. So the things that we are adding together, we have y of t equals. So first the complementary solution, so 1/8 times 4e to the t plus 6e to the minus t, and 4e to the t minus 6e to the minus t. And then we're adding that to 1/4 times 2te to the t plus e to the t minus e to the minus t, and 2t e to the t minus e to the t plus e to the minus t. Combining those together, bringing our fractions in, we get 1/2 e to the t plus 3/4 e to the minus t plus 1/2 t e to the t minus 1/4 plus 1/4 e to the t minus 1/4 e to the minus t. In the second row, we get 1/2 e to the t minus 3/4 e to the minus t plus 1/2 t e to the t and minus 1/4 e to the t plus 1/4 e to the minus t. There are some terms in here we can combine, so we have an e to the t here and here, and we have an e to the minus t here and here. And it's the same thing in the second row. So last but not least, well, second to last but not least, combining those together, we get 3/4 e to the t plus 1/2 e to the minus t plus 1/2 t e to the t. And on the bottom one, we get 1/4 e to the t minus 1/2 e to the minus t plus 1/2 t e to the t. And finally, we can break that out just a little bit. We're going to have 3/4, 1/4 times e to the t minus, plus 1/2, negative 1/2 e to the minus t, and 1/2 t e to the t. And one last simplification here is, well, no, we're just going to leave it like that. That's just fine. All right, so let's call that a day. That's our solution. Y of t equals this thing, a combination. So you'll notice that you have the normal the components of the complementary solution, something that looks like we would expect to see in this kind of situation for if we were doing like method of undetermined coefficients, but it's a little bit different because remember we have to have this secondary term that gets added, and that's why the vector here does not look like an eigenvector associated with the eigenvector lambda equals 1. Just a little bit tricky there. So that is the method of variation of parameters in one worked example. It is a world of bookkeeping. You have to be very careful. I really do recommend going through step by step and trying to keep all of the pieces in their own separate places until you finally bring them all together to use the formula in its full glory. All right, see you all next time, and I hope this